Hi. In this video lecture, we're going to go over a very important theorem in vector calculus known as Stokes theorem. And Stokes theorem deals with computing the line integral of a vector function around a closed path or closed curve C, as shown here on the right. So you've got a curve here. There's a vector field permeating all space. Let's call that F in this lecture. And you want to compute the line integral of that function around that curve C. And that's represented here. Integral with the closed loop symbol means it's a closed curve. Here's my vector field F, and it's dotted. There's a scalar dot product with the integral along that length. So here's an infinitesimal length ds, of which you're computing that integral. This integral comes about, for example, in electromagnetism in Ampere's law, where you're integrating the magnetic field along the closed loop. So the integral of B dot ds, where B is the magnetic field, and that is set equal to, in Ampere's law, to the amount of enclosed current inside that loop. So that's an example in physics where this integral comes about. But Stokes' theorem will deal with transforming this integral into a different type of integral, spoiler alert, to a surface integral, in fact. And that can be very powerful to work out a differential form of the laws of electromagnetism. Anyhow, this is the function or the integral we want to compute. And so that integral in vector calculus gets the name of the circulation. So that closed loop of the vector field dotted with that path is called the circulation integral. Now, to define the orientation of, say, the direction you go around in a loop and the direction, say, of an area vector which is perpendicular to that loop. So let me draw a little perpendicular symbol there. We'll use a right-hand rule to define the direction of the vector area, which is perpendicular to the surface. So that's that vector A coming out of the screen in this case, with respect to the integration direction, which I've chosen to be counterclockwise in that way. So if you imagine putting your thumb in the direction of the integration, which is going counterclockwise like this, then my palm curls in the direction of the area vector. So coming, if it's on the right side of that object, then the area vector is coming up and out. That's why I've shown it this way. So there's a right-hand rule between the direction you're integrating and the area vector direction. Okay. So we have that integral we want to compute. Let's subdivide this surface delineated by the curve C into two regions, C1 and C2. So I've drawn that here, and I've just cut it in roughly half. So here's region C1 and here's region C2, and we can separately compute the circulation of each subregion, C1 and C2. So I have, say, the circulation gamma 1 as the integral over this new closed surface C1, and gamma, well, that should be a 2 here, so let's write the 2. Gamma 2, which is the integral over the second surface. Now, it should be clear that in both cases, this segment between A and B is traversed in both integrals. Now, in one direction, let's take C2, we're going kind of from the top going down to the right. Okay? But in integral for C1, when we go counterclockwise, we're going from the bottom and going up to the left. So they're traversing in different directions, right? And if we imagine, say, our vector field F, which is pointing down and to the right, for C2, if I integrate down and to the right in the same direction of F, that's going to be a positive contribution to the integral. But in the other case, along the same segment, but going around for circulation C1, I'm going up and to the left because I'm still going counterclockwise. And so in that case, F and my integration direction are oppositely directed, and so it comes with a negative sign. So when I add the circulation C2 to circulation C1 to get the total circulation, I'm not double counting that middle piece. In fact, they exactly cancel out. So that exactly equals the total circulation. And so gamma, the total circulation of that bounded surface, is just gamma 1 plus gamma 2, as shown there. Okay. obviously now we can continue subdividing this region into essentially n, where n is large, number of subregions. And so we'll get that the total circulation, no matter how many small regions I draw inside my overall bounded surface, the total circulation is just the sum of the individual circulations of every little subregion. Now what we're going to do is let n get very large so that these subregions become infinitesimal. Okay. All right, so in this case, we let the regions become infinitesimal in size, and we calculate the circulation for just one infinitesimal area, which I'm going to align for the moment in the xy plane. So here's x, there's y vertical, z's coming out of the screen, and here's my infinitesimal subregion, which I'm going to take to be a square. I could just divide any arbitrary shape into a sum of an infinitely large number of infinitesimal squares. All right. And we're going to have to compute the circulation for each one of these individual infinitesimal squares. So we're going to see what we get. I'm going to denote the bottom left corner of my subregion as x naught, y naught in this xyz plane. And we'll talk about the other corners in a minute. Okay, so to find the circulation for this infinitesimal contour, we're going to do a Taylor expansion of my vector field F, which could be, for example, a magnetic field, but also an electric field, about the bottom corner that I've referenced here, this x naught, y naught location, to find the value at the center of each of the 4 line segments. So there's 4 line segments, one in the bottom, the right, the top, and the left. And I'm going to index my function as calculated at this position, x naught, y naught, and then we'll Taylor expand actually in two directions. So it's not just in one variable, but 2, x and y, relative to that point. And so let me discuss how we go through that. A lot of stuff here written down, but let's just do it one step at a time. Let's start with the bottom segment here, starting from x naught, y naught, and we're going to let each of these square dimensions have a length, as I've sort of indicated, but I'll just write it here, delta x along the x direction and delta y along the y direction. Okay. Now what does a Taylor expansion do? We start with the function evaluated at a particular location, say this corner, but I really want to find it in the middle of the bottom segment as my best approximation for what the function is everywhere along that length. Of course, it's a little bit different on the left side and the right side, but for first approximation, we'll just split the line segment in half, and what we'll say is that the value of my function there by Taylor's theorem is a function at x naught, y naught with a correction term, and that correction term is how far did I move in x? I moved by not delta x, but just half of it to get to the center. So delta x over 2 times the derivative of my function with respect to that variable x. So dx. And in fact, it's only the x component of the field that is going to be relevant here. The y and z components, when I do an integral of f dot ds along one of these segments, they're perpendicular. So the scalar dot product of the y component and the z component of the field along the x direction just don't add to f dot ds. It's only f of x times the displacement in x. Anyhow, so for the bottom point, the bottom side, the function is approximately equal to the function valued at this corner x naught, y naught, plus the derivative of f of x at that same place, the slope, times the amount you transport it by, which is delta x over 2. And that gives us an estimation, infinitesimal estimation, for the function f of x at the bottom side. Now, before we move on to y, let's talk about the top side. In this case, we've gone, let's say we're going counterclockwise. We went to the right, we're going to go up, and then we're going to come back to the left along the top side, okay? So we're coming along here at the top, and again, I'm going to approximate my function f of x here right at the middle of the top segment. So you might think, oh, it's exactly the same as before. Well, be careful, not quite. Yes, in x, it's the function f of x at x naught, my field there at this bottom corner. But I need to correct it to halfway along in the x-axis. That's true, just like we did before. But I also have to transport a full width of my infinitesimal square in the y direction, delta y. So I have a transport delta y where I take that times the derivative of my function, my field, with respect to that coordinate, which is y. That's how I get the estimation for my function this top side. I transport both an x and y, x by delta x over 2 and y by delta y. Okay. Now, that was the top and bottom. What about left and right? Let's do left and right. So let's start from the left side. I'm coming back down, say, I want the center of that line segment. So my function here is expanded by the function. And note now I'm not integrating along the x direction anymore. I'm integrating along the y direction. So it's only the field component in the y direction that comes into that f dot ds or f dot dy integral. So now I'm computing f of y, evaluate at the function, at the coordinate x naught, y naught. But to get it in the center of that side, I have to transport halfway up the length of a side. So by delta y over 2, and then times the derivative of the function with respect to y to get the point here. I don't have any correction in x. I'm still at x equals x naught. So that's the only correction in this Taylor expansion of my function. Finally, I want the function evaluated at the right side, f of y on the right. And here now I have to transport not only again in delta y over 2 to get to midpoint in y of my function f of y, but I also have to transport the full delta x value. So I have the same delta y over 2 df y dy added in there, plus delta x times df y dx for the transporting in x. But now we're talking about transporting f of y, the y component of my function, or my field f, not the x component as before. Okay. So the circulation of this infinitesimal loop, if I put all this information together, let me just call it a delta because it's an infinitesimally sized loop. It's the function at the bottom side times the displacement of the bottom side. The function on the left side times the displacement on the left side. Function at the top side times the displacement on the top side, and the function on the right side plus displacement on the right side. At least in vector form. I haven't taken a dot product. Once I do the dot products, I have pluses and minuses, right? So taking that into account, this is going to come in this way, starting from the bottom left. If it's the function along the bottom side times the displacement delta x, that's the contribution to the circulation. Then the function on the right side times displacement delta y. And the function on the top side, but now it's going in the opposite direction, the circulation direction than the function defined in the x direction. So it comes with a minus sign in terms of displacement delta x, and then coming down this side, it's the function in the y direction times the displacement delta y. Again, function is in the integration direction is in the negative y direction. Function y points in the y direction by definition for f of y. So that comes with a negative sign also. So that's taking into account the dot products there. But I still have to plug in for these functions on the bottom, top, left, right that I've computed over here on the left. So we'll do that on the next slide. So that was the contribution, or the calculation for the circulation for that infinitesimal square. But if I plug in here, into the Taylor expansion of f into the circulation, here's what I'm going to get. Okay, and you'll have to just flip back to look at the previous slide to see what we've plugged in. But again, I have, say, starting from the bottom, remember we had along the bottom side the function evaluated at the corner plus a correction to put it in the midpoint. And then that was times delta x in my definition of the circulation. Then on the right side, I'm integrating the y direction. I go to the midpoint, so there's a delta y over 2, df to y, plus the function f of y evaluated at the corner. And then I have to go up to the full displacement in x to get to that right side. And then, okay, same thing for the top and bottom. So here's the top, and then sorry, I said top and left, I should say, and then here's the one for the left. So that's plugging everything in. But we can see a lot of terms which are going to cancel, right? So I have this f of x, x naught, y naught times delta x, and just below it you can see, as I've written, that's going to come in with a minus sign. So that's going to cancel, all right? I even have a delta x times delta x over 2 f of x dfx dx. And again, that's going to cancel here as well. All right. Now, let's look at the other terms. I have a delta y f of y of x naught and y naught. And below it, I have it coming with a minus sign. So adding those together, that's going to cancel. All right. Also, I see that my delta y times delta y over 2 dfy dy, that's going to cancel. Same term down below here. And let's see, and I should have canceled one other one previously. Forgot to cancel that up there. Okay, so what do I have left? I have here one term that's not canceled and one term that's not canceled. I see I have a delta y times delta x times this derivative dfy dx, and I have a minus delta x times delta y times dfx dy here. So my circulation, by adding those pieces together for this infinitesimal loop, is the product of delta x delta y, and then it was dfy dx, so the derivative of the y component of my field f with respect to x minus the derivative of the x component of the field with respect to y. So that's what that boiled down to. And so that's the circulation, and I'll give the circulation a direction which is in the direction of the area vector for that loop. So that'd be the circulation coming out of the page, at least the area vector with the z direction. So the z direction is that combination, that difference of derivatives from the circulation integration times the area vector. What was the area vector? Well, that's obviously delta x times delta y for that square, but we can just call that delta a in the z direction. So the area with the area vector pointing in the z direction. So we've done it, the circulation of an infinitesimal square in one plane. So we've defined infinitesimal area vector in the z direction, as I just said a moment ago. Now, that was just in the xy plane. We can do this for a loop in the yz plane. So first we were in this xy plane. Now I can imagine y and z. In that case, y takes the place of x, so x is going to y in the previous calculation. And z is taking the place of y, so y is going to z. So I take this thing and I just replace with x going to y and y going to z. And that means z has to go to x, so it's an area vector pointing in the x direction. And if I do that, y goes to z, x goes to y, so I have dfz dy time, minus dfy dz, and that's an area vector in the x direction. So that's the circulation in the yz plane. I'll just write down for the xz plane, so that's this plane down below. We can do a similar transformation, and here's what you get. dfx dz minus dfz dx times the area vector pointing in the y direction, because it's going pointing out that way. Okay, what have we learned from all this? Let's go on to the next slide. So summarizing this with vector notation, our circulation for this infinitesimal square was an area vector, but that had x, y, and z components, whether depending which plane you were in and how the area vector pointed. And remember, there was these differences of partial derivatives. So I'm going to write this as a symbol del with a vector crossed with f, the field vector. And that's a function in vector calculus. We've introduced what's called the curl operator. So the curl operator is what I've listed here as del cross f, also written as the curl of f. And it's a combination of all those differences in partial derivatives along each direction. The x direction is the I hat direction, the y direction is the j hat, and the z direction is the k hat direction. And these were the combinations. We just worked out the z component at the very beginning, so that was this combination of differences of dfy dx minus dfx dy, but I also have them here for the other components. I've introduced, that's the definition of the curl operator. You can think about the del in that notation of del cross f here as the gradient operator. And one way to think of it is as the gradient operator is like a vector d dx in the I hat plus d dy in the j hat plus d dz, oops, let's write that as d dz in the k hat direction. And one kind of, not quite a mnemonic, but one symbolic way to kind of try to remember how to write that curl without always having to look it up, but it's perfectly fine to look it up, is there's a trick to, if you know anything about taking determinant of matrices, one way to remember this is a determinant of a 3x3 matrix of vector components of the direction, so I hat, j hat, k hat, my gradient operator, which is d, dx, d, dy, and d, dz, and then the field I'm taking the curl of, so I had f of x, f of y, f of z. So I'm taking a determinant of this strange 3x3 matrix, which really is comprised of operators. But if you know how to do determinants, this might make some sense. If you don't, no worries. Just remember the definition that's written here. But the determinant is like if I take the first row, the I hat direction, I'm working that out. I block that off in the top, first column off, top row off. And then it's d dy of fz minus d dz of fy. And that's exactly what I have there. For the middle part, the j hat, I block off the center column in the top row. It's d dx of fc minus d dz of fx, but because every odd column gets a minus sign, it's flipped, so there's a minus there, as I've said. And then finally for the third column, I block that off, and I have d dx of fy minus d dy of f of x in the k hat direction. And that's how I can write that down. So we've introduced the curl operator here. So our infinitesimal line integral for the circulation can be thought of as this, the circulation, remember, was a closed integral, line integral, so one-dimensional. My vector field f dot ds around that path. That can be thought of as the area vector, infinitesimal area vector dot a, which has a direction, a of I. That was the ith element of the infinitesimal, of the overall field, for the overall surface, if you like, of del cross f, or the curl of f. The total circulation will be the sum of all those infinitesimal contributions, so those I number of infinitesimal squares, where I gets to be can sum over a very large number. So I'm summing from I to n, where n is going to become very large. I have to sum and add all those curl contributions. And so what I've done is in the infinitesimal limit, where delta ai becomes infinitesimally small, this sum of a bunch of infinitesimally small areas becomes a surface integral. And so what I've really done is I've transformed my original circulation, which was a line integral, a closed path line integral, of my vector field along a path C dotted with ds along that path. I've transformed it now to the sum of all these curls, so here's the del cross f, dotted with an area vector, and I'm integrating over the surface of that shape that's closed by the path C. So path C defines some sort of arbitrary shape. The surface of that shape is the surface integral here on the right. And so what Stokes' theorem has done is it has transformed an integral of a vector function, the line integral of that along a closed path, into the surface integral of the curl of that vector function over the whole surface. And that'll be very useful when we work out in the laws of electromagnetism how to go from integral form of those equations to the differential form. But what we've done is we've gone up to an extra dimension in the integration from one-dimensional to two-dimensional, but at the expense that we have a derivative in there in this curl operator, which is a strange operator, but it comes up in physics, particularly in the laws of physics, so it's very important. Okay, that will end this lecture on Stokes' theorem. Oh, and this is just to stay, state in words on the slide what I just closed with. It transforms a line integral of a vector function into a surface integral. All right, that again, this ends that lecture.